We'll discuss a few more examples on linear independence, and then we'll proceed for the discussion on linear combinations. We'll see a few more examples. So consider the vector space P2, which is nothing but the set of all polynomials with degree 2. I can write as this. So x of t as that t is basically the variable over which the polynomial is defined. Summation I equal to 0 to 2 some alpha I multiplied by t to the power I, where alpha I belong to R for all I is a vector space T2 over the field of units. Now consider we let X be a set of two vectors. The first vector is 1 plus 5t square, let us label it as V1. The other vector is 7 minus t square, let us label that as V2. Question is this set of vectors linearly independent? So how do you solve for this? Consider a scalar alpha from the field of years and a scalar beta from the field of reals. Take this combination alpha v1 plus beta v2, equate it to 0. Now we have to solve for alpha and beta. If the solution is such that alpha and beta have to be 0, then we can conclude that the vectors v1 and v2 are linearly independent. So what we have is alpha 1 plus 5t square plus beta 7 minus t square to be equal to 0. From here what we can get is alpha plus 7 beta should be 0 and 5 alpha minus beta should be 0. If you solve this, we essentially solving this, right? 1 7 5 minus 1 to be equal to 0 0. If we solve this, what we get is the only solution that this system has is alpha equal to 0 and beta equal to 0. So V1 and V2 are linearly independent. Let us consider another set. Let us label that set as Y. 1 plus 5t square 7 minus t square, and then let's say one more vector 2 plus 3t square. The vectors v1, v2 and v3. Is this set of vectors a linearly independent set? Are v1, v2, v3 linearly independent? So we'll take this combination again, where alpha, beta, gamma, belong to the field. I'll just correct this. Alpha, beta, gamma belong to the field. If we replace V1, V2, V3, what we essentially get is alpha 1 plus 5t square plus beta 7 minus t square plus gamma 2 plus 3t square has to be a zero polynomial. So from here we essentially have alpha plus 7 beta plus 2 gamma to be equal to 0, and then we have 5 alpha minus beta plus 3 gamma to be equal to 0. Now let's solve this. I'll label this as equation 1 and this as equation 2. From equation 2, what do you have? Beta is equal to 5 alpha plus 3 gamma. Now if you substitute this relationship between beta and alpha in 1, what you get is alpha plus 7. Instead of beta, you'll have 5 alpha plus 3 gamma coming up, then plus 2 gamma to be equal to 0. So this gives me 36 alpha plus 23 gamma to be equal to 0, which means gamma is minus 36 by 23 times of alpha. And from here we get beta to be equal to 5 times alpha minus 3 into 36 by 23 times of alpha, which is 7 by 23 times of alpha. So what do we get here is alpha v1 plus beta v2 plus gamma v3 goes to 0 for the given vectors v1, v2, v3 if beta is 7 by 23 times of alpha and gamma is minus 36 by 23 times of alpha. So apart from the solution where alpha, beta and gamma are zeros, we have non-zero solutions for which alpha v1 plus beta v2 plus gamma v3 goes to 0. Hence v1, v2 and v3 are linearly dependent. They are not linearly independent. Okay. Similar process can also be adopted if you are given a set of 2 cross 2 matrices or a set of 3 cross 3 matrices, and you have been asked whether the set of vectors that you are given are is a linearly independent set or not, or the vectors that you have are linearly independent or not. Okay. So if the sum of the scaled versions of individual vectors when equated to 0 results in a solution where all scalars turn out to be 0 and that is the only solution, then the given non-zero vectors are essentially linearly independent. If it is not, if the scalars, if there is a solution where the scalars can possibly be non-zero, then the set of vectors is going to be linearly dependent. Okay, now in a vector space, given a vector, you can always find a set of vectors. So if V belongs to the vector space V defined over the field, over some field F, suppose you take up a vector, then there exists a set of vectors Wi in the vector space itself, such that V can be expressed in terms of this set of vectors. Okay, this is something that we call as linear combination. Okay, so every vector in the vector space V over the field F can be expressed as a linear combination of other vectors in V, provided they are not linearly independent. Now, when we say they, what does this they mean? This means the vector that you choose to express. So, the vector V in the vector space, this, and the vectors with respect to which you want to express V. These two should not be linearly independent. So this the set of vectors in terms of which you want to express V and V, all these together should not be linearly independent. They should be linearly dependent. Only then you can express V as a linear combination of W. Now what is the meaning of linear combination? Essentially, you can express V as summation of the scaled up versions of the vectors Wi. Okay, so here alpha i's will belong to the field F, V and Wi belong to the set V or the vector space P for all I and the set V and Wi, it's a linearly dependent set. Okay, some examples. Suppose the vector space considered is R3 and the corresponding field that I am considering is R. Then in that case, let's pick up a vector. Let's say that it is 2, 3, 10. Okay. Now consider the set of these vectors: 1, 0, 0, 0, 1, 0, and 0, 0, 1. In the three-dimensional space, you would normally label them as the x, y, and z axis correspondingly. Okay. So what you have is W1, W2, and W3. So V, W1, W3, if you can verify, all the four vectors here are going to be linearly dependent. So here I can express V as 2 times W1 plus 3 times W2 plus 10 times W3. Okay. Let us choose another set. Let's say it is 1, 0, 0, 0, 1, 0, and 1, 0, 1. So if you verify again, considering this as W1, W2, and W3 respectively, you can verify that V, W1, W3 are linearly dependent. So I can express V as some alpha W1 plus beta W2 plus, or rather, let's use alpha 1 W1 plus alpha 2 W2 plus alpha 3 W3. Can you find out what this alpha 1, alpha 2, alpha 3 are? Please try to solve this. Similarly, if you consider a vector space which is a set of 2 cross 2 real matrices with the field R, choose a V which we can have, let's say 1, 5, 6, 9, and a set let's say 1, 0, 0, 0, 0, 1, 0, 0. Express V as a linear combination of W1 and W2. Okay, so here you can verify that V, W1, W2 are linearly independent. Okay, so we cannot express V as a linear combination of W1 and W as a linear combination of W1 and W2. Now what if for the same V we had taken V equal to 1, 5, 6, I guess we took 9. And let's say that the set of vectors is 1, 0, 0, 0, 1, 0, or rather 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So we have W1, W2, W3 and W4. So V is 1 times W1 plus 5 times W2 plus 6 times W3 plus 9 times W4. What if the set of vectors that you are given with is this? So what will be V in this case? You can express this as probably 2 times W1 plus 5 times W2 plus one simplest way rather is 1 times W1, 5 times W2, 6 times W3, 9 times W4 plus 0 times W5. But what if you want this value to be non-zero? Essentially solve for a set of simultaneous equations. So I'll express V as alpha W1, alpha 1 W1 plus alpha 2 W2, alpha 3 W3, alpha 4 W4, alpha 5 W5. Okay, so what I get is alpha 1 plus alpha 5 to be equal to 1. Then here I get alpha 2 to be equal to 5, and I have alpha 3 to be equal to 6, and then I have alpha 1 plus, oh not alpha 1, alpha 4 plus alpha 5 to be equal to 9. Alpha 2 and alpha 3 values seem to be fixed at 5 and 6 for this. You can solve for alpha 1 plus alpha 5 and alpha 4 plus alpha 5. So if we solve these two, what we get is so this one will give me alpha 5 is nothing but 9 minus alpha 4, and if I substitute it here, what I would get is alpha 1 plus 9 minus alpha 4 is 1, which essentially says alpha 4 is equal to alpha 1 plus 8. Okay, so with alpha 1, alpha 2 to be equal to 5, alpha 3 to be equal to 6, alpha 4 to be equal to alpha 1 plus 8, and alpha 5 to be equal to I guess it is 1 minus alpha 1, right? If we substitute alpha 4 here, we get 9 minus 8 minus alpha 1. If we have this, then we can be expressed as a linear combination of these 5 vectors. So if we set alpha 1 to be equal to 2, so let alpha 1 to be equal to 2, one possible linear combination that you get is 2 times w1 plus 5 times w2 plus 6 times w3 plus 10 times w4 minus 1 times alpha 5. Okay, so v can be expressed as a linear combination of these vectors. Can you express v as a linear combination of w1, w2 and w5? Okay, please verify this. Also check can you express v as a linear combination of w2, w3 and w5? Okay, please check these. We'll stop here. Thank you.